Welcome. My name is Jana Kierdorf and I'm a PhD student at the University of Bonn. I work mainly in the area of agricultural and environmental sciences, and my talk is about what identifies a whale by its fluke on the benefit of interpretable machine learning for whale identification. I want to start with the motivation why to use explainable and interpretable machine learning and sciences in general. In this figure, you can see the basic machine learning pipeline. We take any kind of geodata, find a suitable machine learning model, and as a result, get our model output. Now, it's often difficult to explain or interpret the results scientifically to get a scientific outcome. To derive an explainable machine learning model, there are three core characteristics which play an important role. There is a certain transparency where you can have access to the model component and maybe also the motivation why a specific design was chosen. Furthermore, interpretability and explainability play an important role in the process to improve the results. You have interpretability either of the model or the output, for example, when you interpret the output by means of the input through a heat map. And then you have explainability, which needs domain knowledge. Given all these, you can get an outcome with a scientific value, and deriving scientific outcomes without domain knowledge is barely possible. You might have already noted that I distinguish between interpretability and explainability. We realized that there is no unique definition of explainability and clear distinction to interpretability. So this is our thought about it. You can have one interpretation, but changing with the application, you might come up with different explanations. But now to the question why explainable machine learning should be used. I think explainable machine learning can help us in many areas of different sciences, and the scientific value of a result can be increased by increasing reliability and trust, for example, or by deriving novel scientific insights and scientific discoveries. In our work, we focus on the question, can we use the idea of Lapushkin about the unmasking of clever hands predictors for whale monitoring and protection? But have in mind that it can also be applied to many other research questions with photogrammetric and remote sensing data. But now to the whale monitoring. Whale populations are threatened by commercial whaling, ocean warming, and competition for food. So additionally, it's important to monitor whales and spatial temporal migration. This is done by looking on many close-range images taken from tourists. In these images, specific whales are identified, and this is currently still done manually, and experts look primarily at corners of the fluke, also called fluke tips. The shape or spatial features such as scars or color pigmentations. We use the given dataset of humpback whale images, and this is provided by the Kaggle challenge humpback whale identification. And the aim is to identify which image represents which whale. The dataset contains about 66,000 images, where each whale has an ID, and each ID corresponds to a class. In total, there are 10,008 classes, and since each whale is a class in itself, there are 10,008 different whales in the dataset. Additionally, there is a reference for each image given. In the dataset, however, one encounters certain challenges, such as the strong variations that are spread over the entire dataset, as for example the color space like RGB or grayscale, the image size, the resolution, or the time of day, or the percentage of the visible whale, and much more, as you can see in these example images. And to find an automatic solution for this task, a Kaggle challenge was created a few years ago, in which several thousand whales are to be assigned with only a few images. It was not surprising that the three winning solutions are neural networks. And we took a closer look at the second winning solution and thought about how interpretability and explainability of models can help us to better understand results and check the quality of the model. In the case of the used network, a resident 101 with a weighted sum of 3 loss functions is used. For this purpose, we have looked at 2 interpretation tools that visualize processes in the neural network and their decision by means of heat maps. Occlusion sensitivity maps determine how much the output changes if you cover part of the input. So now it's interesting to see which areas exactly speak for a specific whale and also if this agrees with the experts. Here, for example, the right area at the Fluke tips are very distinctive for this particular whale, which is highlighted by the green areas. Another tool is Garcke, which looked at the gradient in the network. You can see that this procedure indicates that this small notch is very important and is crucial for identifying the whale. What we did in particular is we took all heat maps and clustered them with spectral clustering and analyzed which heat maps are in each cluster. We've calculated the heat maps in respect to the top 5 predicted classes per image, and all of these are included in the clustering. I have selected a few examples that represent some of the clusters. Cluster 1, for example, contains heat maps in which the total area of the fluke represents the respective whale. Cluster 2 contains heat map that focuses on the pigmentation near the fluke tips. But compared to the other 2 clusters, the heat maps in cluster 29 do not have any distinctive features. The clusters in the upper figures correspond to the cluster numbers on the x-axis in the lower plot. And for this plot, we have now selected the heat maps corresponding to the reference class and plotted their proportion of the respective cluster. The different colors can be ignored for the sake of simplicity. So, as you can see, it turned out that some types of heat maps are associated with very high detection rates and some are not. This means that if the network is looking at certain characteristics of the fluke, then it can be said how reliably the network can detect this whale. So what did we find out? We had some results with high scores, but the cluster was actually indicating that you must be careful with the results. Therefore, the score of the network does not always reflect the cluster assignment, and this can enable a real-time evaluation of a photograph, for example, regarding the lighting conditions or the viewing angle. That means domain knowledge is not only used for explaining, but already to obtain more scientifically and hopefully better solutions. Another aspect is that currently most of the interpretation tools are applied post hoc. That means the choice of the machine learning model, for example, the neural network architecture, and the choice of the interpretation tool are independent of each other, which can lead to limited possibilities for explanations. Also, currently explainable machine learning is mostly used to prove or find hypotheses, which are already known to us, but it would be really cool if it could provide us with hypotheses which could lead to novel scientific discoveries. So we could ask whether we can come up with other definitions. To sum up, we gain insights into which features are relevant for the decision of the network in the context of whale identification, and we can conclude that the interpretation tools confirm the researcher's statement. I see a huge potential of explainable machine learning kind of science for every kind of geodata. However, the requirement is to work interdisciplinary. And we would like to see more people working at the interface of machine learning and some kind of application area. Thank you for your attention, and if you have any questions, don't hesitate to contact me via this mail address.